Good evening, and welcome to the Scientific Adventures of Beardman. Today we're going to begin a unit on astronomy, or astrophysics. Today we're going to look at the introduction of that, which will kind of end up focusing on telescopes, because the first thing, if we're going to learn about what's out there in space, we have to understand how we can learn about it. And really, for the most part, all we've got is the ability to see space. Yeah, we've sent some spacecraft out to Mars, Venus, the Moon. We've sent people to the Moon. We may send people to Mars in the near future. But at the moment, outside of our solar system, at least very far out of our solar system, we haven't even been able to send a craft. All we have is the light that's come to us. And so being able to understand that light and being able to gather that light and analyze it carefully is very important. And that's essentially what telescopes do. Some people think the primary purpose of telescopes is to make things bigger. I think a clearer purpose for a telescope would be to say that the telescope is designed to make things easier to see. And there are a couple ways you could do that. You can make things that are invisible to our eyes visible, or you can make things that are already visible more clear. Okay, so there are two purposes if we're talking visible light, but two things a telescope really wants to do well. One is magnification, make it bigger, and then the other is resolution. Resolution makes it easier to distinguish between two things that are close together. For example, if you're driving down the road at night on the highway to Northern California or Arizona or Vegas, and up in the distance a car is coming towards you. And you're like, wait, that's a motorcycle. It's only got one light. But then as it gets closer and closer, all of a sudden you can see that there are two headlights. That's because far enough away, your eyes don't have enough resolution to be able to distinguish that those are different objects. And it's only when it gets closer that your eyes have the ability to resolve those two headlights and make it clear that they are separate objects. And so that's what a telescope does. One thing it does is take something where we look and we just see one dot, and we are able to resolve that, wow, that's actually a galaxy with hundreds of billions of stars, and it just looked like a dot to us because it was so far away. So those are the two things that a telescope does. Okay, later on we'll talk about also how you can design telescopes that help allow us through digital recordings to recognize light in ranges of the electromagnetic spectrum that we can't see. But first, let's get more into how a telescope can help us to magnify and resolve light. Well, first of all, if you've ever been in a dark room, okay, where there's maybe a tiny bit of light, because if there's no light, you can't see anything. But if there's a tiny bit of light, but you just have trouble seeing it, there's just not enough light for you to be able to make out what it is that you're looking at. Well, what happens when you're in that dark room? Your pupils, okay, your eye right there, the pupil of your eye, the black part in the center, it gets bigger when it gets dark. Let's see if we can do that. Okay, make it dark. I hope my eye is getting bigger. Okay, and we make it bright. We see it gets smaller. We aren't really going to focus so much on why it gets smaller right now, but we'll focus on why it gets bigger. Well, it gets bigger because that black part, the pupil, is where it's collecting light. Okay? And so when it gets bigger, it's able to collect more light. And it funnels it to the back of my eye where I can see it. If it gets bigger, I can see more light. I'm able to see a little bit better in a dark room in low light conditions. A telescope does that same thing. A telescope, instead of making our eye go to about 1 centimeter across, which is a surface area of about 3.14 centimeters squared in area. A telescope can instead make our eye 100 centimeters squared, or 1,000 centimeters squared, okay? Or much, much bigger, okay? Could be a mile across, okay? And give us an incredibly big telescope. You could have what we'll talk about is an array of telescopes that allows you to resolve as though your eye was incredibly large. So with just your eye, you look up at the sky and you see a star that's so far away you can't actually see it. Your eye may gather a few photons, but not enough to stimulate the rods to allow you to see that faint object. So the telescope is a much bigger area, so it can gather a whole lot more light, and then the telescope has to have something so that large amount of light that it gathered can be funneled into my eye. Okay? So how do we do that? Well, we know we can bend light, like you saw in the refraction video. We can bend light using something with a higher index of refraction, like a piece of glass. So if we take a piece of glass and we bend it, okay, and shave it off, make it into a lens, well then as the light comes in, it bends, and we can bend it, funnel it into my eye. Okay, and that allows me to get all of that light, so I can see a fainter object, get it all funneled into my eye. We call that kind of telescope a refracting telescope, because the light is refracting through the air to glass interface and the glass to air interface. Okay? Usually they have more than one lens, but we aren't going to get into too much detail in this particular video. There's some problems with this kind of telescope. You know, making binoculars or a spyglass that a pirate would use. Those aren't too hard. You get a piece of glass and you just polish it nicely. But if you want to get like a really big refracting telescope to collect a lot of light to see a distant galaxy, well, if you've got this huge piece of glass that has to get thinner towards the edge, it has to be really thick in the middle, that's going to make it really heavy, and you've got to hold it out here at the end where it's fragile and thin, and it makes it very hard to deal with and expensive because you got so much stuff. You got to polish both sides of that. And as we learned when we learned in the rainbow video, different colors of light bend different amounts. So the red light from the star will end up in one place, while the violet light from the star will end up in another place. This is called chromatic aberration. And it's obviously a terrible situation to have if you're trying to view what the star looks like. It's going to distort it, and it's going to destroy your resolution by sending different colors to different places. So, 200 years ago, I guess, Isaac Newton came up with another idea. He said, hey, I know another way to change the direction of light. I can bend it using refraction through a lens, but I can also bounce it off a mirror. Well, why don't I just get a curved mirror and bounce the light off of it, and I can focus the light that way and funnel it into my eye using a mirror. Okay, well, great idea. Way to go, Newton. So he's got the Newtonian telescope, okay, which also called reflectors or reflecting telescopes. And reflecting telescopes are great because you can support the back of the mirror. You can even build it into a mountainside, make a big cement dish, and then put a reflecting surface over that. And you can make it huge. And it's supported from the back. You've only got to clean one side. You've only got to polish one side. I think I just said the same thing. Oh well. And it's just easier to make. So using a Newtonian telescope, a reflector, a reflecting telescope, we're able to make these incredibly large telescopes and able to collect a lot of light and funnel it to our eyes. Okay, now of course we don't always want to funnel it to our eyes because we often want to record it. So just like your cell phone has cells in it that detect light, and we use that as a camera there, you can put the same type of camera, more sophisticated, into a telescope and record that information and you can store what you're seeing to be able to be analyzed by a computer or whatever for a long period of time. Also, we don't have to just record what's in the visible range. We can record all the other ranges. We can record everything from radio waves, microwaves, infrared, visible, ultraviolet, X-rays and gamma rays. All of those can be recorded using telescopes. Okay? We just need different materials. For example, for radio waves, you don't have to use a mirror. You can just use a piece of metal, okay, like a big satellite dish, right? Okay, the radio wave comes in, the metal bounces that radio wave to the center of the funnel, okay, called the focus, and that allows us to see radio waves coming into Earth from space. Now, unfortunately, there's a problem with looking from Earth. We referred to this in our refraction video, okay, that as the light's coming from the sky, the stars are twinkling, shimmering around because the air is changing densities. Well, how can we avoid that? Well, if we go up to the mountains, then we're above a lot of the air. There's not as much, especially if we go to a remote area, there's not all the heat being produced from cement and stuff like that, so there's less heat waves, so to speak, you know, where there's different densities in the air, and that makes it a little bit clearer. We can also go to the desert where everything's more similar. There aren't, you know, cars and houses and everything that produces all this other stuff. There aren't as many differences in the density of the air above you. Also, when you go to a remote area, you remove light pollution. We're trying to collect a small amount of light. If we've got a lot of light streaming in from a street light next to us, well, we're going to collect a lot of that light, but it's, you know, bouncing off molecules in the air, bouncing off dust in the air and stuff. So we'll collect all that light, but that'll wash out the little tiny bits of light we're trying to get from distant galaxies. So we move to remote areas, ideally on top of a mountain where there's less atmosphere above us, ideally in a place that's not too cloudy, so we don't have to shut down the telescope for clouds. But there's another problem. Even if we go to a place like that, it turns out our atmosphere blocks a lot of the light. Visible light comes through pretty well. So do radio waves. These are what are called our atmospheric windows. But gamma rays are blocked high up in the atmosphere. Ultraviolet are blocked. Most ultraviolet is blocked by the ozone layer. Water vapor absorbs microwaves and part of the infrared. So if we want to be able to see infrared coming from space, or microwaves coming from space, or gamma rays coming from space, we got to go to space. And that's the first most famous space telescope was the Hubble. Okay, getting up above the atmosphere gets rid of all that distortion, all those molecules that can block out the light, and we can see the light coming straight in, which I guess is a much better view of what's going on. So that's our introduction. We're going to, in the next videos in this astronomy series, we're going to be looking at what we learn from that light that we gather using telescopes. All right, take a little bit to go outside and look up and see what it is we're studying. Enjoy the beautiful sky. We'll see you next time on the scientific adventures of Beardman.